Okay. So we'll talk about CFTs, and there's going to be some elementary stuff, some more advanced stuff, hopefully something for everyone. And so at a very basic level, so basically CFTs in D larger than 2 dimensions is a simple subject compared to CFTs in 2 dimensions. So the structure is not so rich, so you have limited set of tools, and you have to know how to get around using those tools. And but you have to understand well why those tools work. And so I'll talk to you a little bit. I'll start by talking to you about some basic rules of the game, which at some level you can just buy. But I'll try to explain then in the second part of why these rules are actually sensible and why they have something to do with physics. And then, based on this acquired knowledge, we will see how to introduce some deeper rules, and those rules will eventually allow us to do the bootstrap. So at the very basic level, CFT is just a quantum field theory whose correlation functions are invariant under the conformal group. And in these lectures, we will only consider CFTs in Euclidean RD. So there are going to be no subtleties related to topology. There's going to be no subtleties related to Minkowski signature. There's going to be a lecture course about Minkowski CFTs later on. And so first of all, what are the conformal transformations? So conformal transformations of RD are some maps x to x prime equals f of x, which are supposed to be 1-to-1. And they have this property that locally they look like a dilatation and a rotation. So locally, dilatation and rotation. So if you have a point x and it's mapped, so you consider some neighborhood, there's some basis in this neighborhood, and you map it to a point x prime. So this neighborhood becomes larger, but it's still a circular neighborhood, and there is some rotation of the axis. 6 prime. So we express it by saying that if you write a Jacobian matrix, G mu nu equals df mu dx nu. By the way, since we are in the Euclidean, I'm not going to indulge in typographical delights, and I will keep no distinction between upper and lower indices. So this Jacobian matrix, it has to have the form of some function omega of x, scalar function, times some matrix R mu nu of x, and this matrix R mu nu is supposed to be an orthogonal matrix. So it's an OD matrix, so R transpose is equal to 1. So that's the definition of the conformal transformation, and these transformations, they clearly form a group, and this group includes Poincare, dilatations, and that's the whole point. It also includes some other transformations. So for the moment, I'm going to leave it at that. We are going to talk about conformal group more in a second. But let me now talk more about CFTs. So then the next step is that in any CFT you will have a bunch of fields, phi of x. So we will call interchangeably these fields or operators. These are just synonyms, local operators. So I is just an index which numbers all these fields, 1, 2, 3, and by convention, the first of these fields is the identity. And each of these fields is going to be characterized by two labels. So the first label is going to be scaling dimension. And this is just a real number, delta I, a positive real number. So for the identity, we will have the dimension is 0, and for all other fields, the dimension is positive. And there's going to be a second label, which is going to be rho I, which is an irreducible representation of SOD. So basically, all our fields are going to transform in some representation of SOD. They can be scalars, they can be vectors, tensors, symmetric traceless tensors or antisymmetric tensors. And they're also going to be, they can also be fermions, transformed in spinorial representations. But in these lectures, for simplicity, I'm not going to talk about fermions. I'm only going to talk about bosonic fields. So there are some subtleties for fermions as usual. And so with these fields, we have to say that correlation functions of our theory are invariant. So what does this mean? So let me consider some correlation function of a bunch of fields, phi 1 of x1, phi n of xn, and I'll just denote it as a function g, which depends on x1, xn. So conformal invariance of this correlation function is going to be a generalization of scale invariance and of Poincare invariance. So for scale invariance, scale invariance of this correlation function just means that if you take g of lambda x1, lambda xn, then this would be equal to lambda to the power minus delta 1 minus delta 2 minus delta n g of x1 xn. This is what we mean by scale invariance with scaling dimensions delta I. So conformal invariance is going to generalize this as follows. Let me assume for the moment that all of these fields phi 1, phi n are scalars. So for phi I scalars, we will have the following relation. So if we have this transformation x goes to x prime, then the correlation function at the points x1 prime, xn prime is going to be related to the correlation function at the points x1, xn by this factor omega of x1 to the power minus delta 1, omega of xn to the power minus delta n. So you see that for a scale transformation with parameter lambda, omega is exactly equal to lambda, so this equation reduces to this. For a general x-dependent omega of x, this is clearly a more general relation. And so we are going to express this equation by saying that the field phi I transforms as phi I tilde of x prime equals omega of x to the power minus delta I phi of x. Phi I. Yeah. So you see, what do I mean by this phrase? So in fact, phi I tilde here is exactly the same field as phi I. It's just it sits at a different point. So what I'm saying by this equation is that if we evaluate correlation functions of phi I tilde, which is the same as phi I, then we will get the same correlation functions as the correlation functions of the fields in the right-hand side. That's all I'm saying. So for the moment, this tilde is just here to remind us that about this transformation, but in a second it's actually going to be more useful. Okay. So now let us suppose that phi I are not scalars. So in some irreps rho I. So in this case, the transformation property of the correlation function is going to generalize those of the Poincaré transformations. So for invariance under Poincaré, so Poincaré means x prime equals Rx plus b with some constant matrix R. So in this case, the transformation rule is very simple. It just says that phi tilde of x prime equals rho of R phi of x, where this rho of R is a finite dimensional matrix which acts on the indices of field phi and which represents this matrix R. So this is the representation of R which acts on indices of phi. So for example, if phi is a vector, then phi tilde of x prime, for example, if phi is a vector, then phi tilde mu of x prime is equal simply R mu nu phi nu of x. So now we have to generalize this, and the generalization is going to be as follows. So for conformal transformations, this is going to be generalized as phi tilde of x prime equals omega of x to the power minus delta phi rho, which depends on R of x, phi of x. So in other words, you take the conformal transformation. The conformal transformation gives you these two objects, omega of x and R of x, and then based on this R of x matrix, which is x dependent, you construct the corresponding matrix rho of R of x, you act with it on the field phi of x, and that's your transformation. So fair enough. We have our basic rule. We say that the correlation functions have to be invariant under this replacement. But clearly, okay, you can buy this, but if you see it for the first time, this clearly raises a lot of questions. So you may wonder why conformal invariance? Why should we expect that our theories should have conformal invariance? Why do we have this weird transformation property, weird or natural depending on your perspective. And what does this have to do with physics? So gradually, over the course of these lectures, we will understand all of these points. Okay. Now the next part is going to be, I'm going to talk about conformal transformations in more depth. And here, so again, the basic ideas are pretty easy. You have to do a bunch of calculations. I'm going to leave out most of these calculations as exercises. So I'm going to put lecture notes and you will see what these exercises are. So I encourage you to do them. There's really no advantage for me to do this on the blackboard. So let me first give an equivalent definition of what a conformal transformation is. So sometimes we also say that conformal transformations leave the metric invariant up to x-dependent factor. So what this means is that dx prime squared is equal to omega of x squared, where omega is the same as over there, times dx squared. So exercise number 1, you should convince yourself that this is equivalent to the other definition that I gave. But this should be kind of clear from the picture that I drew, that there are these two neighborhoods which are both circular. And so the length of dx prime is proportional to the length of dx. So now there comes a theorem. So there's a theorem of Liouville, which tells you what are the possible conformal transformations in RD. So it tells you that conformal transformations in RD are generated by translations rotations, dilatations. We already considered those x prime equals lambda x. And to this list, which is pretty obvious, you have to add just one transformation, which is inversion. Which is given by the formula x prime mu equals x mu divided by x squared. So this theorem is true for dimensions d larger than 2. And so here comes a second exercise. Convince yourself that inversion is indeed a conformal transformation. So you take these basic transformations, you take all their possible compositions, and you get a group of conformal transformations, which is a finite dimensional Lie group. Now, this finite dimensional Lie group has some topology, and the inversion transformation belongs to the component of this Lie group which is disconnected from the identity. So inversion is disconnected from the identity. So we would like to understand, to begin with, the connected component of this Lie group. And for this purpose, we introduce something which is called special conformal transformation. So it's SCT, which depends on the vector A, which is an RD vector. And it is defined as a conjugation of translation by inversion. So we take, so this inversion is I, given by this formula. So I take inversion and compose it with translation. For convention, I take the translation with the vector minus A, and again with the inversion. Since I used the inversion twice, this thing now belongs to the connected component. And in fact, connected component of the conformal group is generated by translations, rotations, dilatations, and the special conformal transformations. So now, so if you want to do this CFT in D larger than 2 dimensions, you have to familiarize yourself with this SCT. In particular, you have to compute what it's like. And so the formula is this, so SCT of A, it sends x to x mu minus a mu x squared, 1 minus 2 ax plus a squared x squared.
If you're looking at the conformal transformations on R to the D, isn't it just the connected component because the inversion doesn't map the origin to anything? So it's only the special conformal transformations that are modified.
You have to talk a little bit about infinity, but notice that even the special conformal transformation also maps some points to infinity.
Yeah, okay.
So I'm going to talk about infinity for a second, but thanks for raising this point. You can pose this question locally. You can say, let me look at the neighborhood of RD and let me ask what are the conformal transformations there. And even in that case, Liouville theorem applies. Any other questions? So, okay, now this is the group. The next natural question when you have a group is to discuss the Lie algebra. And, well, it's very easy. We consider infinitesimal transformations, conformal transformations, and then we consider infinitesimal conformal transformations so x prime equals x plus epsilon of x. And so we consider the vector fields epsilon of x, which parameterize this infinitesimal conformal transformations, and this is the Lie algebra. And so the Lie algebra of this conformal group is going to consist of generators P mu, M mu nu, which are the Poincare generators. There's going to be the dilatation generator D. And there are going to be this K mu, which are special conformal transformation generators. And so we just have to work out the corresponding vector fields. So for P mu, the vector field is just D mu. I denote the vector field with small letters. So M mu nu is x nu d mu minus x mu d nu. The dilatation vector field is x lambda d lambda. And finally, the special conformal transformation vector field, which you obtain by taking the infinitesimal version of this SCT. This is more interesting, so it's equal to 2x mu x times d minus x squared d mu. And so one thing that you should visualize is what does this k mu actually do? So if you draw the line of flows, the lines of flow of this k mu, for example, let's take k1. Then you get the following picture. So there's the origin is kept fixed, and then there are this kind of circles which come back to itself, and the vertical axis is just pushed to infinity. So you can say a few things here. One thing that you can say is that by considering the infinitesimal version of the requirement that the conformal transformation preserve the metric or up to a constant factor of that equation, you can show that, and this is the exercise, you can derive conformal killing equation which has to be satisfied by all of these vector fields. So the conformal killing equation says that d mu epsilon mu plus d nu epsilon mu equals 2 over d times epsilon. And in fact, by using this conformal killing equation, you can show that in d larger than 2, there are no other conformal transformations apart from the ones that I already wrote down. Delta mu, yeah, thank you. All right. Well, what do you do next? Now that you know the Lie algebra, you derive the commutation relations of the conformal group. And so I'm not going to write them down completely, but you'll find them in the notes. But basically, the commutation relations so the rotation commutation relations are just the commutator of m with m. It gives you m as usual. Then the commutation relations of m with p, it gives you p. And this just means that p is a vector under rotations. Then m with k is again k. So k is also a vector with under rotations. But then there are 3 more interesting commutation relations that tell you how k and p commutes with d and how k with p commute among themselves. So those ones I will write down in detail. So d pm equals pm, d km k mu equals minus k mu, and finally k mu p nu equals 2 delta mu nu d minus 2 m mu nu. So these are the computation. Okay, this might be a boring computation, so let us try to get most out of it. So what does this computation tell us non-trivially is that you can think of this dilatation generator as measuring the dimension of your generators. And so all the other commutations that I did not write down, they're 0. So it means that you can think of the generators M and D having dimension 0, the generator P mu having dimension 1, and the generator K mu having dimension -1. And all of these commutation relations, they preserve this grading by the dimension. And you can also think by going to the expressions of the generators, you can also understand the dimensions of various generators by counting the number of x's and the derivatives. And you see that K mu has 2 x's and 1 derivative, and that's why it has dimension -1. And so the whole non-trivial power of the conformal group will come from having this generator of dimension -1. Because if you have only P mu, you can only, if you act with P mu on fields, so you differentiate fields, this raises dimension. But now we'll have this new generator K mu, and if we act with it on fields, we'll be able to lower dimension. So this is non-trivial operation, and that's why it's going to become powerful. So we have this finite dimensional Lie algebra, and now all finite dimensional Lie algebras are classified. So we might ask, what is this algebra that we are dealing with? That's a natural question. And the first thing we can do is to count the number of generators. So how many generators do we have? So how many generators? So we have d times d minus 1 over 2 from M, from rotation generators. Then we have one generator which is dilatation. We have d generators P and d generators K. So if you do the algebra, you'll get d plus 2 times d plus 1 over 2. And so the number of generators is the same as for SOD plus 2. But actually, as a real form, this Lie algebra is not SOD plus 2, but it is SOD plus 1, comma 1. Now, this fact can be seen in several ways. So the most direct way to see it is to find just linear combinations of generators that I wrote down in such a way that those linear combinations, they will satisfy the commutation relations of SOD plus 1, comma 1. Now this is a boring way. I'm not going to do it. There is a somewhat more illuminating way, which is once you know the answer that it has to be SOD plus 1, comma 1, you can say, well, where does SOD plus 1, comma 1 act? Well, it naturally acts on RD plus 1, comma 1. So a smart way to establish this correspondence is to consider the basic action of SOD plus 1, comma 1 on the Minkowski space D plus 1, comma 1, and somehow manage to find within this action the action of the conformal group. So it's possible to do this, and this is the basic idea of the so-called embedding formalism. Which we might discuss later on in these lectures. So what other comments can you make here? So it is very important that the conformal group is the conformal algebra and the conformal group is a simple group. So from the point of view of the algebra, it just means that there's no subset of generators which is left invariant by the Lie brackets. And again, this property is only true because we added this K-mu generator to the game. For example, if you remove the K-mu generator, if you only consider Poincaré and the dilatation, which would be scale invariance, then the algebra is not simple. And in that case, you do have scale invariance, but it basically buys you nothing. So you don't have any interesting constraints on your theory. And so that's why conformal invariance is much more powerful than scale invariance. Okay, so let me recap. So we have conformal group, we have connected component of the conformal group, and so now I would like to make my definition of the CFT more precise. So by CFT, we mean a theory which is invariant under SO d plus 1, 1, so connected component. So the theory might or might not be invariant under the inversion. So this is an extra requirement. So invariance under inversion is an extra discrete symmetry that some CFTs may have and some CFTs may not have. So this is inversion invariance may or may not hold. So when is it going to hold? For that we have an interesting criterion. So this is an exercise show that inversion I is conjugate to parity transformation by SOD plus 1, 1. So parity, by parity transformation, let me call it like blackboard P. So it sends x1 to minus x1 and it leaves x2 up to xd invariant. So we have two discrete symmetries that our conformal field theory might or might not have. Invariance under inversion and invariance under parity. But since inversion and parity are conjugate, it means that they either both are present or both are absent. So a CFT is invariant under the full conformal group, OD plus 1, 1, if and only if it is invariant under parity. Well, it means that there exists a SOD plus 1, 1 transformation G such that I is equal to G minus 1 PG. The G is in the connected component. SOD plus 1, 1. Okay, so one last thing that I have to discuss is what is the question about the infinity. So here I was glib about infinity, but you can see that we have to say something about infinity. So inversion sends 0 to infinity and vice versa. Special conformal transformation, if you look at the denominator, there exists a point x equals a over a squared, which is sent to infinity. So why is this happening? Well, you can think of this happening because this vector field K mu, you see that it has x squared behavior at infinity. So the coefficients of the vector field K mu have very rapid behavior at infinity, and so when you exponentiate K mu, it's like solving the equation, the differential equation y prime equals y squared, which blows up in finite time. So for this reason, the special conformal transformation maps some points to infinity. So what do you do with this? So, well, if you want to treat this properly, you have to say that conformal transformations act not on RD, but you have to add to RD one point, RD and infinity. So this is sometimes called Riemann sphere. Now, if you want to be completely rigorous, what you do is the following. You take your metric, Euclidean metric ds squared, and you rescale it. So you introduce a new metric ds squared nu, which is a rescaling of the old metric by some constant, by some x-dependent factor w of x. So this is called Weyl rescaling. So why would we like to do this? Well, for two reasons. The first reason is that since the conformal transformations are defined as transformations which preserve the metric up to an x-dependent factor, it means that if we rescale the metric by another x-dependent factor, then at least locally this does not change anything about the class of conformal transformations. So Weyl rescaling does not change the set of conformal transformations. On the other hand, if you choose this metric w of x appropriately, you should be able to arrange it in such a way that the point infinity is now a finite distance away. So if you just add to this point infinity to RD, it's a bit awkward because it's infinite distance away. So we cannot consider it as a proper Riemannian manifold. But let us choose w of x so that x equals infinity is finite distance away. So for example, w of x, we can choose 1 over x squared at infinity. It doesn't really matter what it is at finite x. And then you work on this Riemannian manifold, which now includes legitimately includes the point infinity, and the set of conformal transformations is the same. So in fact, so here I said that w of x can be arbitrary up to this behavior at infinity, but you can also, for the sake of beauty, what you can try to do this is an exercise. So show that by an appropriate choice of w of x, you can arrange that the new metric ds squared nu is standard metric on the round d-dimensional sphere SD. So this is the origin of the terminology Riemann sphere. So this is the first part of the exercise, and the second part of the exercise is to show that you can also choose the metric ds squared nu to be the metric on the cylinder, and by the cylinder I call the manifold SD minus 1 times R. So this is a very important manifold that we will encounter later on.
You have to do a corresponding transformation in your field.
For the moment I'm just talking about geometry. I'm not... Yeah, so the question was if I'm also transforming the fields. I would have to transform the fields if I talked about correlation functions. For the moment I'm just talking about geometry. I'm saying that we can transform, we can find a Weyl rescaling so that the metric, Euclidean metric, becomes equivalent to the metric of the sphere or to the metric of the cylinder. I'm not trying to put field theory on those manifolds yet. Any other questions? Okay, so now that we know a little bit more about the group structure of conformal transformations, we can come back to this question: why this weird transformation rule for the operators? So I wrote this rule Let me write it again. So phi tilde of f of x is equal to omega of x to the power minus delta phi, rho of r of x, phi of x. So I would like to separate the discussion into two parts. So first of all, let me forget that phi of x is a field of a conformal field theory, but let me just consider this transformation as a transformation acting on functions. So for step one, so imagine that phi of x is just some function on Rd, and I take this function and I transform this to another function phi tilde by this formula. So why is this an interesting thing to do? So we have this map, let me call it pi f, which takes a function phi and maps it to the function phi tilde. So it's a function phi which takes values in V rho, which is the vector space of the irreducible representation rho. So the interesting thing about this map is that this map is a representation of the conformal group. That might be obvious for some of you, but let me state it explicitly. So this is a representation of conformal group. So we said the conformal group is SOD plus 1, 1. So it's a simple group. So it has, of course, some finite dimensional representations. being a group of matrices. But here I'm considering an infinite dimensional representation of conformal group acting on functions on RD. So to check that this is a representation, you of course have to check that if you compose two conformal transformations, then this also composes properly. And so this I leave it to you as an exercise. So check this. But basically, maybe you should not be too surprised that this is going to be a representation. So it's basically going to follow from the fact that if you compose two conformal transformations, then the Jacobi matrices, they also compose by the chain rule. And so this factors omega of x will compose properly, and the matrices, rotation matrices R of x will compose properly. And basically, you will get that this is indeed a representation. So let me denote this representation as P, delta, and rho. So this representation depends on two numbers, on the finite dimensional representation rho of SOD, and on the scaling dimension delta of delta phi of the field phi. So now I'm going to step 2. I'm going to go back to the correlation function. So I'm going to consider now correlation function g of x1 xn, which is the same one as I wrote before. So it's a correlation function of phi 1 x1 phi n xn. And whether I'm dealing with the conformal field theory or not, I can take this correlation function, which is a function of n variables, and I can act with the conformal group. Since the conformal group it's represented on functions of x, now I have function of n variables, so conformal group acts on such functions. And so this correlation function of n point correlation function, it belongs to the tensor product representation pi delta 1 rho 1 tensor product pi delta 2 rho 2 it lives in this representation. So this is a triviality. And now there comes a non-trivial point. Since if now my theory is conformal, then this correlation function which lives in this representation is not just any element of this representation, of this tensor product representation, but it is an invariant tensor. So I have to take all elements of this representation and I have to fish inside them for elements which are invariant under the section, and then I will get correlation functions of the conformal field theory. So, in other words, in group theory language, what we have is the following statement, that correlation function of CFT is an invariant tensor inside tensor product representation. So this hopefully goes some way towards explaining why the structures that we introduce are natural. But that's not yet everything, because I have not yet explained why that particular representation. So what is so special about that particular representation? So why this representation? And here I would like to point out two specific things about this representation, two special things about this representation. So two special things. So the first thing is that in the right-hand side, I only have omega and r, but I do not have anything which depends on the derivatives of omega and on the derivatives of r. So this representation somehow it is very local. It depends very locally on the structure of my conformal transformation. So only omega and r, but not their derivatives. And the second thing, which is actually related to the first, is that in the right-hand side, I only have, so phi tilde only depends on phi, but it does not depend on any other fields. Now you can think, okay, how else could this be? And okay, here I have to finally admit that I was being a bit cavalier. So this transformation property is not going to apply to all fields of our conformal field theory. It's only going to apply to primary fields. So this will apply only to primary fields. And in order to convince yourself that not all fields are primaries, is very easy. Let's suppose that the field phi is a primary field. So let me consider an exercise. Suppose that phi is a scalar primary. And let me take another field which I will denote v mu, which by definition is going to be equal to the derivative of phi. Well, it's a field in my theory. Somebody just gave me the field v mu and did not tell me that it's the derivative of phi, but just gave me this field v mu. And you would like to know how will it transform. Well, the transformation rules of v mu can of course be worked out from the transformation rules of phi very trivially. So you just have to take this equation, you have to differentiate it in x. So what will you see? So the exercise is to work out the transformation rules of v mu, and you will see that it will schematically have the form. So v mu tilde is going to be schematically as something v mu plus something else phi, and that something else will involve derivatives of omega and r. Well, not r because this is a scalar. So it will violate both of these special things, special properties. And so now we see that in the conformal field theory we'll have some fields which are primaries. Then we'll have some fields which are derivatives of primaries. Derivatives of primaries. Which are called descendants. And the derivatives of primaries are definitely not primaries themselves. And now we have a problem because you would like to know if for some reason there are some fields which are neither primaries nor descendants, because descendants by themselves are not a problem, because if you say, okay, if a field is a descendant, it does not transform in a simple way, but who cares, because I will learn everything I need to know about descendants by studying corresponding primaries. It would be a problem if they were a field which is neither descendant nor a primary, but here there is a fact that in the CFT any field is either a primary or a descendant of primary, or a linear combination. Thereof. Now, at this stage, this fact is not at all obvious, but we will get to the point where it will become kind of obvious.
Are you assuming unitarity?
I'm assuming many things.
Yeah. Can you repeat what the question was?
So the question was whether this fact relies on some additional assumptions, like unitarity or something else. And yes, there are some hidden assumptions here, and I'm going to state these assumptions later on. But in fact, this fact is much more generally true. It's true not just for unitary theories, but also for a big class of non-unitary theories. All right.
Sorry, can I ask you something?
Yeah.
So far, our definition of a primary is something that transforms as that.
Yeah. That's going to be the definition of a primary.
Okay.
There are going to be some equivalent definitions
Right.
later on. Yeah. Any other questions? Yeah.
Is your fact, when you say descendant, do you mean fields that are only single derivatives of primaries?
Oh no, they're going to be derivatives of any order. Of any order. Sorry. Thanks. Okay, so what is missing from this whole picture? Well, many things missing. What I discussed so far, like correlation functions and correlation functions transforming under conformal group and being invariant, this is something which is usually called kinematics of conformal field theory. And this is enough to discuss certain things. For example, you can already start working out simple constraints on 2-point functions, 3-point functions, 4-point functions which follow from these kinematics. I might mention this later on. But this would not be enough to do the bootstrap. So to do the bootstrap, we need to inject some extra ingredients in our discussion, such as state operator correspondence and the OPE. So to understand where this comes from, we will have to introduce locality in our discussion. So far we were just viewing our conformal field theory as a bunch of correlation functions invariant under conformal transformations, and it was not clear where those correlation functions coming from. So we would like to impose in some way a requirement that our theory is local. So this is something that we will have to explain what this means. And also, when we do this, it will allow us to explain why conformal invariance. So conformal invariance, why do we have this fact that many theories have conformal invariance? So this again is ultimately related to locality. So let me formalize this last point a little bit. So what it means to show that our theory is conformally invariant. So we would like to show, would like to explain to show conformal invariance. And I formulated conformal invariance as invariance under finite conformal transformations, but now that we know these infinitesimal vector fields, we know the conformal algebra, you can of course restate everything as an invariance under infinitesimal conformal transformation. It's going to be completely equivalent. So let us do this. So what do you need to do for that? We have to take that rule, which is the rule for transformation of the primaries under finite transformations. I started with this rule for finite transformations because actually it's, as you see, it's a representation of conformal group which can be written rather compactly in that formula. But now I would like to take that rule and I would like to rewrite it as a transformation under infinitesimal conformal transformations. So of course what we need to do, we have to take f of x equals x plus epsilon of x, where epsilon is one of the conformal killing vector fields. We substitute it, so substitute it into star, to that equation star, and work out the transformation property. So I'm going to leave it as an exercise that the transformation property is going to look like this. Phi tilde of x is equal phi of x plus some quantity over the epsilon that I will denote as q epsilon times phi, which also depends on x. And q epsilon, which is a function of epsilon, it's given by this equation, q epsilon times phi. It's equal to epsilon times d plus delta phi over d, the divergence of epsilon, delta times epsilon, plus minus 1/2 d mu epsilon nu s mu nu phi of x. So here S mu nu are the matrices of the representation in which phi transforms. So these are representation matrices of the representation rho in which phi transforms. So in particular, if phi is a scalar, then this term is absent, and there's no term. So if you wish, I could write it like, suppose that phi has some indices. Let me write like phi b, and then these matrices have two indices a, b. I could write it like that. So now this is an exercise. So this is infinitesimal transformation, and now if we know the infinitesimal transformation, we can of course write down the invariance property in the following form. So our invariance property, so that G is invariant, so this is equivalent to the following equation. So we take Q epsilon, we acted on phi 1 of x1, phi 2 of x2, and so on. We act with Q epsilon on every phi, plus phi 1 of x1, Q epsilon phi 2 x2, and so on. So we take the sum of all of these terms, and they have to sum up to 0. So this is the infinitesimal form of the invariance under the conformal group. So what we have to do, we have to explain where these q epsilons come from. So that's going to be our next task. Any questions?
Got about 4 minutes.
I got about 4 minutes. Yeah, good. So, well, maybe then I can give a preview of what's going to come next. So, I'll in order to understand this, so these are lectures about CFTs, but in order to understand this and to understand locality, it will be nice to make a detour into theories which are not necessarily conformal. So I'm going to talk a little bit about UV complete quantum field theories and explain how we think about these objects. So there are actually two ways to think about UV complete quantum field theories. So there's one probabilistic way to think about them and one operatorial way. So we'll need both of these ways. I will talk a little bit how mathematicians think about them, and in particular I will focus on some aspect which has to do with fields being random distributions, which is something that physicists don't usually think about. And eventually we will introduce the stress tensor, the local stress tensor, and it is, the way this question is going to be answered, q epsilon, is that we will construct this object q epsilon in terms of the stress tensor. And among these q epsilons there are going to be some q's which correspond to Poincaré generators and the dilatation generators, and there's going to be one corresponding to the special conformal transformation generator. And so basically the way we should phrase this discussion is why, if Poincaré and scale generators exist, why should the scale special conformal transformation generator also exist? And this will end up being a certain property of the stress tensor operator of the theory. So this goes under the name of scale invariance implies conformal invariance. And once we understand that, we will understand why conformal field theories are ubiquitous, because scale invariant field theories are fixed points of the renormalization group flows and are ubiquitous. So this is going to be the plan for the first part of the next lecture. I think I'll stop here.
Any other questions? We have a couple minutes. This question.
So the infinite dimension representation we consider here, do we know if they're completely reducible or not? So like if that tensor product is completely reducible?
So the question was, what do we know about this representation being reducible or irreducible? So this representation is going to be irreducible.
Right.
Yeah. Now to talk about reducibility of the tensor product, it's a bit of a subtle question, because this representation is not a unitary representation of the conformal group. So I'm not going to discuss this reducibility. I'm not sure this is even well defined mathematically, because there is no like nice topology on this representation. But the representation itself is definitely irreducible. Any other questions? Okay, well, see you on Wednesday then.
So this is your lunch break. We'll convene back here at 2 p.m.